Hello everyone. I am making a video of this PowerPoint, which I will also share with you in Google Classroom. Please feel free to just follow along until the very end, where we'll go over some practice problems. This is rather difficult to fully wrap your mind around, but the good news is that it's not extensively tested on the AP exam, nor is it extensively tested in college. So I wanted to make a quick video rather than assigning book reading. So just stick with me, regardless of how frustrated you may feel, because this is not the easiest to wrap your mind around. And in fact, when you do go back in college and revisit this theory, I'm sure you'll struggle with it then too. So don't lose confidence. Just hop on this train, and I'm going to explain this as best as possible. You can find this in chapter 11 in your textbook if you do want to do some follow-up reading, and it's called valence bond theory. It's also known as hybridization. And I'm going to start out with ammonia as my example because ammonia is a simple molecule and it will elucidate why this theory was needed. When you think about ammonia, you think about a nitrogen and two hydrogens, and these are the atomic orbitals. Nitrogen has 3 electrons that are in its 2p orbitals that are unpaired, and the reason why ammonia forms as a stable molecule is simply because this hydrogen, one hydrogen fits here, another hydrogen 1s electron fits here, and a third fits here. And when this happens, each hydrogen fills its orbital of 2, and the nitrogen completes its octet by becoming p6. Makes sense. However, it's when we think about their geometry that the problem arises. When you think about the s and the p orbitals, we remember that s orbitals are spherical, but p orbitals are not. And I'm looking right here at the carbon's 2p orbitals, and they're all pointed along the vertices, right, of a Cartesian coordinate system. And if you were to overlay these on one point of origin, they would have 90-degree angles from one another. The problem is when you look at ammonia or any other molecule, very rarely are you going to get a geometry that corresponds to these atomic orbitals. And Linus Pauling chose to explain this, or attempted to explain this, with what's known as valence bond theory, also known as hybridization theory. And how he accounted for the sort of difference in between theory and practice is, which I'm talking about here, how he accounted for the difference between what we observe in nature versus what the atomic orbitals predict should be the geometry is through hybridization. And it's very important that you understand that we're talking about internally hybridization happens. Hybridization happens internally on atoms and molecules. So here are the tenets. Internally, atoms or molecules internally may mix at least 2 non-equivalent or different orbitals, for example, s and p, to create hybrid orbitals that have a different shape from the original atomic orbitals. What we'll also find, it's not just a different shape, but they point along different axes than the original orbitals. Point number 2, the number of hybrid orbitals is equal to the number of pure atomic orbitals used in the process. Meaning, if a central atom mixes one s and one p, it gets 2 hybrid orbitals coming out. If you mix 3 orbitals internally, you get 3 coming out that are hybrids. Whatever you put in is what you get out in terms of number. And lastly, covalent bonds are the result of hybrid orbitals on one atom or molecule overlapping with atomic orbitals on another, or hybrid and hybrid overlapping. Here's what we mean by atoms mixing or hybridizing their orbitals. Now, this is what's happening with ammonia, NH3, and methane, CH4. This is how the tetrahedral geometry is achieved. sp3 is the name of a hybrid orbital, and the superscript, if it's not written, is understood to be 1. So 1s and 3 p's were mixed to produce 4 sp3 hybrid orbitals. Notice you see 1, 2, 3, 4 orbitals on the right, and p superscript 3 plus 1 of the superscript s gives you 4. So if you see sp3 hybrid orbitals, you not only know what went in, but you know how many of them there are by adding up the superscripts. So this is what happens. Internally, so for example, our N of the ammonia mixes 1 of its S's and 3 of its p orbitals and produces 4 hybrid orbitals. These orbitals are all equivalent in shape, but point along different axes. If you were to overlay these, what you find is they point to the vertices of a tetrahedron. 4, 1, 2, 3, 4 electron pairs around a central atom in nature forms a tetrahedral shape. This is that shape. This carbon forms a tetrahedron because rather than using its unhybridized s and p orbitals for bonding, it hybridizes internally and produces sp3 hybrid orbitals, each of which point along the vertices of a tetrahedron. And I'd like to go back to point out one more thing. These hybrid orbitals all have major and minor lobes. Notice in the picture, it's not even showing the minor lobes. It's only showing these major lobes, and that is because those are where the majority of electron density are found, and that's where the bonding occurs. Here's an example of carbon hybridizing its internal s and p orbitals to produce sp3 orbitals, and it produces 4 of them, and the hydrogen atoms are bonding through technically their unhybridized 1s orbitals. Ammonia, the reason why it is close to a tetrahedron in shape, but a little off, is because with ammonia having 1, 2, 3, 4 repelling units, one of which is non-bonded, it forms a tetrahedral shape, and it achieves this tetrahedral shape just like methane by mixing 1 s and 3 of its p's internally to produce 4 of the equivalent sp3 hybrid orbitals. The reason why it's not a perfect tetrahedron, the lone pair, which is existing in one of these hybridized orbitals, is more repellent than the bonded pairs, which of course increases this angle but decreases this angle. And the angle that's always referenced is the bonded angles. So with lone pairs, right, we never talk about a lone pair angle. We look at what the molecular angles are by actually bonded atoms. So this, instead of 109.5, will be less than 109.5, and it's actually around 107. Now, in the previous example, this is called sp3 hybrid orbitals. Now, what about shapes such as linear, trigonal, planar? Well, you don't always put all of the p orbitals into the hybridization. You always do put the s though. So when you have a linear shape, it is the result of only mixing 2 atomic orbitals. When you only mix 1 s and only one of those p's, you end up getting 2 sp hybrid orbitals. And if you overlay them on the same point of origin, that would be right here in the middle of this beryllium. And when you do this, they point not at the vertices of a tetrahedron, but at 180 apart. What if you mix not just one p, but two p's? When you mix S and two p's, this is how you get trigonal planar shapes. Notice sp2, the 2 and the 1 add to 3, and we get 3 orbitals. Overlaying them on the same point of origin, like this middle of this boron, gives me a trigonal planar geometry. When you have sp2 hybrid orbitals, they point at 120 degrees apart, and they form the trigonal planar shape. So, how do you predict what's the so-called hybridization around a central atom? You do it last. First, you make its Lewis structure, and then you determine, well, from its Lewis structure, what is the electron pair geometry? Again, we don't just count the bonded, but also the non-bonded. So it's the total electron pair geometry. If the central atom has 2, then it's linear. And the hybridization on the central atom is sp. If it is 3 electron pairs around a central atom, regardless of whether they're all bonded or not, you have sp2 hybridization. If there's 4, like in the case of both our carbon with 4 hydrogens, methane, as well as our nitrogen with 3 hydrogens, ammonia, as well as with water, you have sp3 hybridization because this is the hybridization that corresponds to a tetrahedron. They can be all bonded, 3 bonded, and 1 non-bonded, or, as in our case of water, 2 bonded, 2 non-bonded. As long as there's 4 repelling units, it forms a tetrahedral electron pair geometry. The molecular shape may be different, bent, trigonal, pyramidal, and tetrahedral, but the hybridization is all the same because the tetrahedron is the parent shape for all of these. You can even throw some D's into the mix. Notice that 1 plus 3 plus 1 is 5, and notice that 2 D's gives you a 6. So you figure out the Lewis structure first. If it's trigonal bipyramidal in electron pair geometry, then it must be sp3d, and if it is tetrahedral, it must be sp3d2. So if I were you, what I would do right now is reopen my VSEPR theory activity from the last class, and I would write these as a new column or just on the left to the bond pairs. Because what we have here is if these are our steric numbers, this is the geometry this is the hybridization happening on a central atom associated with that. One thing we don't have explained yet are double bonds. And here is where this notion of unbonded or unhybridized, I shouldn't say unbonded, I should say unhybridized p orbitals comes into play. So what happens when we don't mix all of the p orbitals? Remember how there's sp, sp3, sp2? Well, not all the p orbitals have to go into the mix. And when you have additional p orbitals that haven't been mixed in, they remain unhybridized. So let's take the case of carbon. This is its normal electron configuration, 2s2, 2p2. When hybridization occurs, one of these s electrons gets pushed into or promoted into the 2p because they're a little bit higher energy, so we often use the word promoted. But what if only 2 of these are mixed with the s orbital? One of them remains unhybridized. So if you mix 1, 2, and 3 orbitals, you get 3 out, all of which are sp2 hybrids. And this lone unhybridized p still remains. It's going to be used for double bonding. Here's how it looks. If these are the three sp2 hybrid orbitals forming that trigonal plane, perpendicular to it is the unhybridized pz orbital. And this is how we explain the bonding in a molecule, ethylene. Now, ethylene has 2 carbons and 4 hydrogens. It has a double bond in the center, not just a single bond. The single bond is formed by the hybrid sp2 orbitals from each carbon sharing this space of overlap. And this is called a sigma bond, in part a sigma bond. Sigma, not single, although both are true. SIGMA. And this is called a sigma bond, and the characteristic of a sigma bond is spherical or circular overlap. Each of these carbons could be rotating or spinning such that these hydrogens are coming in and out of the plane of your screen. They maintain contact because of the carbon-carbons maintain a bond in contact because of this spherical relationship. Single bonds allow for free rotation like this. The double bond is formed by the unhybridized 2pz orbitals on both carbons. They can overlap above and below the plane of our sigma bond. This is technically a second bond, but double bonds, even though they have 2 points of contact, are still considered one bond. So don't get confused by this. This still represents a double bond, but only one of them, even though there's 2 points of contact that result from the fact that a p orbital is dumbbell shaped, and we're not overlapping in a head-to-head manner. You can see it here. Although it may look like it's 2 double bonds, it's still just a 1 double bond. And this is what's called a pi bond. A pi bond has 2 points of contact. Again, the molecular geometry of this can be quite confusing. When we consider the amount that this is likely to be represented on our AP exam, and hence, whether or not it's worth, the week we could spend really drilling down into these concepts, I honestly say what we're going to do is I'm just going to show you how to focus on the essentials. So next, I'm going to show you how this applies to problems that you would encounter on the AP exam, and I'm going to pare it down to the bare essentials. If you wanted to read more and you have the time to dig deeply into this concept, you certainly can at the beginning part of chapter 11 in your textbook. But what I'm going to show you next is really the part that you're essentially responsible for. So this is the part where I really would like you to take some notes, because here's the application of what's known as hybridization or valence bond theory.